In this video lecture, we're going to try to summarize everything we know about circuits so far. So, first thing we have is the EMF device shown here. It's represented by something that looks like a capacitor. One side is a little longer than the other to represent the plus side, and the shorter side is the minus side. Here I've drawn the current to go up, but of course you can define the current to go anywhere, to go up or down. You might think this is counterintuitive, but one way to think of it is if you had two batteries, then the potential might be going the other way if B was connected to a much stronger battery, so forcing the current to go through the minus side. So if we analyze a circuit going from A to B, then that is from minus to plus, then the voltage drop we get will be plus E because we gain potential. Now we can also analyze the other way, and going from B to A, in which case we go from plus to minus, and we'll have a negative potential drop, and that'll be minus E. So you see, it doesn't depend on the direction of the current, just the direction that you're analyzing, which leads us to this simple statement. The voltage drop does not depend upon the direction of the defined current, just whether you go from plus to minus or minus to plus. Now let's look at the resistor. Here, the voltage drop will depend on the direction of I. So here I have a resistor between A and B. I've defined the current as going from A to B. Now, analyzing from A to B, the voltage drop will be given by Ohm's law. It'll be, you lose potential because going from A to B along the direction of current, it's going to give you minus IR. If we chose to analyze going from B to A, however, we gain potential. It's like running the movie backwards. Delta V will be equal to IR. So this gives us a simple statement. The voltage drop, in this case, does depend upon the direction of the defined current. The next thing to know about resistors is that when you put them in series, like so, you get two voltage drops for the same current. The first one will be minus IR1, and the second one will be minus IR2. This means that for the resistors in series, it's the same current but different voltage drops. And of course, the equivalent resistance for resistors in series is very simple. You just add the two. So in this case, R1 and R2 is replaced by a resistor R12, which is simply the sum R1 plus R2. Now, for resistors in parallel, because they're in parallel, they'll see the same potential drop. So we have delta V1 across R1 is the same as delta V2 across R2. And it's the same Ohm's law for each of them. This gives us the statement, very simple statement of that the same voltage drop, you have different currents for resistors in parallel. The equivalent resistance for resistors in parallel, of course, is you sum the reciprocals and take the reciprocal, given by this formula. Moving on to capacitors, the voltage drop across the capacitor is a very familiar delta V equals Q over C. And when you have capacitors in series, you will have two voltage drops for each capacitor. One would be delta V1 and the other would be delta V2. When capacitors are in series, they have the same charge. So from this, you can get using the voltage drop equation, get the voltage drop across each capacitor. So for capacitors in series, we also have a very simple statement, which is for the same capacitors in series have the same charge but different voltage drops. And of course, the equivalent capacitance for capacitors in series is is similar to resistors in parallel. You sum the reciprocals and take the reciprocal as such. For capacitors in parallel, they share the same voltage, and from the same voltage drop equation we can get the charge that would appear on each capacitor. This leads to, again, another simple statement for capacitors in parallel, which is capacitors in parallel have the same voltage drop but see different charges. And of course, for the equivalent capacitance, it's very simple. It's just adding the two capacitances, and it's analogous to what you would do for adding resistors in series. So capacitors in series and in parallel are opposite for resistors in series and in parallel. There are a couple more things we should know about capacitors, and that is when you first connect the voltage to a capacitor, the capacitor can be replaced by a short circuit. That is, it can be just replaced by a straight line. This only occurs at the moment you put voltage onto the capacitor, because at this moment the charge on the capacitor, it hasn't been charged, so there's no charge. Q equals 0. The voltage drop, since there's no charge, is also 0, but the current will not be 0. So only at t equals 0, when you first put voltage on a capacitor, can you replace the capacitor by a simple line. Now, if you wait a long time, that is when t goes infinity after you hooked up the voltage to it, or in other words, they use the word steady state. When you wait for a steady state situation, you have a situation where you can replace the capacitor by an open circuit. That is just two leads to represent that there is a break in the circuit. Now, the charge now will be the familiar voltage drop for a capacitor, Q equals CV, and in this case, since it's an open circuit, there can be no current flowing through this capacitor, so I must equal 0. The next thing we learned is what's called the loop rule. That is, the sum of all the voltage drops around any closed loop in a circuit must be 0. So suppose we have this circuit here. We have two batteries, E1 and E2, and I get to define direction of current any way I want. So in this case, just for fun, I'm going to have I1 go against this battery, going this way, I2 go down along R2, and I3 going up along R3 and going to the left like this. So in this circuit, I can see two loops, loop 1 and loop 2. We want to apply the loop rule to each of these loops, and for loop 1 we have I can go around any way I want. I can go around clockwise or counterclockwise in analyzing this loop. So just for fun, I'm going to go counterclockwise like this. So when I go around counterclockwise, let's say starting at this point and I go down the battery, I lose potential. That's why I have a minus E1 here, right? And then as I go up, I'm going against the current. So instead of the usual minus I2R2, I have a plus I2R2. And then as I go along here, I'm going with the current, so I have a negative I1R1. And that, since it's around the loop, must equal 0. Now, for loop 2, I choose, just for fun, to go around clockwise, to go around this way. So starting, say, at this point, I'm going against the current. I3 is actually going up, but I'm going to go against it. So I get a positive I3R3, and I go from the battery from a plus to minus, so I lose potential. I get minus E2, and as I go up R2, I'm going against the current, so I get a plus I2R2, and that all must equal 0 as well. Now, we didn't talk about this in class, but we don't necessarily need to go through a loop to find a voltage drop between any 2 points. So we can choose any 2 points and find the voltage drop between those 2 points. So for example, if we go to the circuit we just in the previous slide, choosing and ask us ourselves what would be the voltage between A and B, we could write something like this. Starting at voltage A, it would be have voltage of A VA, and as you go clockwise along R3, you get a positive I3 R3 drop, and then you go across E2, you get a minus E2, and then you arrive at voltage at B. So this whole side must equal the voltage at B. We can also go the other way, going counterclockwise, and same thing. We start at VA, and this time we go down R2, so we get a minus I2 R2 drop, and then we are going to arrive at the voltage at B, going counterclockwise. So we really don't need to go around a whole loop. We can just go from A to B, defining the potentials at A and B. Finally, we have our last rule, which would be the junction rule, and that is, pick any junction. The sum of the currents going into that junction must equal the sum going out. So looking at our example circuit again, if we looked at the junction at point A, for example, then we see that I3 is coming in from the left into that junction, and I1 plus I2 are leaving that junction. So I3 must equal I1 plus I2. And again, I get to define any direction for the current. So as long as I'm consistent with everything else, it should all work out. Okay, so that's all the time I have for now. I hope all of this helps. Goodbye.